What's up, YouTube? Today we are going to go over part 2 in this series about writing our own interpreter in OCaml. Once again, this is with theinterpreterbook.com. I know Primogen has abandoned this project, but don't worry. I'm not going to leave you hanging high and dry like he does. So let's just go over a quick recap of where we've been, and we're going to go over a little bit what it means to start writing a parser. Let's head straight to it. Where we left off last time was we had created a lexer. And what you should think about for a lexer is you start off with something like let x is function y, z, and then return y plus z. What a lexer does is when you have your lexer, or sometimes it's called a tokenizer, or there's various different words for it, but we don't need to get too lost in the details for that. That basically says, let's turn this into something like, okay, we have a let keyword, then we have like ident x, and then we have something like an equals, and then we have something like a function, and then we have a left parent, and then we have an, ident y, we have a comma, we have an ident z, and you can sort of see how the rest of this goes on, right? And the general idea being here that we get rid of all the things that aren't important. So in monkey lang, white space isn't important, so we don't need to keep anything about that. And then eventually we get all of these characters. Now, this is nice. This moves this from just sort of like a random string, not super helpful, to this stream of tokens, which is actually pretty helpful, right? Because now we can start sort of classifying these. And if you remember the tokens that we have literally something like this where we say an ident, and that can hold a string. And we also have things like a let, or here's a function, or we also added keywords for true and false and if. We're not going to go over those today, right? But basically, our first part, a lexer, you can imagine all it does is it takes this string and then you get out a list of tokens. Phase 2 of the steps that we want to do is we're going to work on making a parser. And so what does the parser do? A parser should take basically a token list, and we want to turn that into basically like a tree. Sometimes you'll have heard this called an AST, which stands for abstract syntax tree. Right, that's what this means. And this basically just says, like, instead of having this, what we really want to have is something like, okay, what we have is a let statement, and the name is some x value, right? And the value is something like, okay, we have a function, right? And the function has args, y and z, and the body is a return statement with the expression being something like left side is y, we're gonna add these, and the right side is z, right? Something like this. You can sort of imagine that that's what we're trying to shoot for. And so ultimately, our goal with this is we want to turn this into a structure that later we'll be able to evaluate, right? So first phase is lexer, second phase is parser. We go from this flat list to like a tree that has sort of more or less the kind of semantic meaning that we're trying to encode with what we're actually writing. With that in mind, let's go ahead and check out the type of the thing that we're trying to generate. Now remember, this may look a little bit crazy at first. There's a few extra things going on in the file. We're not going to cover everything. I want to give you this sort of picture of what our end goal is that we want to try and do. And the picture that we have here is that we have some node, which represents the kind of thing that we have in a file. In the previous example, it would be one statement. This is one complete let statement. We say let x equals this function. Okay, that's one complete statement. We can actually look at what our statement type looks like, which is says, hey, here's all the statements that we support today. You could add more of these. You could add a macro statement, or you could add whatever you want to do. That's part of the fun of writing your own language. But in this case, what we have is a let statement, and we say we have some identifier, that's this x, and then we have some value, that's this expression. They say, what does expression look like? We go into expression and we see a lot of things that we expect, right? You could have an identifier. That's just like a variable, right? Or just literally an int, or literally a Boolean, or a string. And then we get into something that's a little bit complicated. And if you're interested, I can try and maybe do a more deep dive example into this concept of Pratt parsing in the next video. It would definitely have to be its own whole video. So if you want that, let me know in the comments and maybe we can work that out. But the general idea here, you'll see just like how I wrote that we have this sort of concept of returning an expression with the left side being a y and then an addition and then a right. What we have here is we have this infix operation where we have some expression on the left, some operator, and then some expression on the right. So that's how we would get to this expression inside of this statement. However, what we have is not just a statement cipher, we actually have a whole function. Oh, sorry, let me say it again. However, what we have here is not just one addition expression. What we actually have is a complete function. So we can see that we have a different variant. Once again, you can think of this as enums or whatever you want, right? You could have literally an expression that's just an identifier, or we have this more complicated expression, which is a complete function literal. And just like I wrote out before, probably uncoincidentally, right? This idea of a function having some arguments, and the only things that you're allowed to have are identifiers, and then you have some body, which is a block. You say, well, what's a block? Let's just go check. A block is a list of statements. What's a statement? Well, that's the thing we already looked at, right? And in this case, we only have one kind of statement, which is a return statement, and a return just holds an expression. If you think about it, when you have a return, it always just has one expression here that needs to get evaluated later. So you say sort of this one thing here is a complete statement. We can make it of the variant type return, and it holds this expression. And then we go back in and you can see how these types sort of interleave with each other. But it's very cool to be able to see sort of this concept of how that's working. So you could return another function. We don't have to do a bunch of extra work to do that because we're already handling that functions are inside of an expression. We're already handling that functions are inside of an expression. So if we did something like return foo, and then that's going to return y plus z plus foo, see how we didn't have to do any extra work to manage this concept. This whole thing is one expression, and we look at our return, it just says a return has to hold an expression. So it's totally fine that we have a return statement, which holds an expression, which can hold another return statement. Nobody is scared of that in the type system. Maybe you're scared looking at it, but I promise if you think about it for a little bit, you can sort of see how that goes. And that concept is unpacked more in the book, as well as this concept of Pratt parsing. So like I said, if you want to see it, we can try to do that. So that's the AST that we're trying to build. How then, though, do we go from a stream of these tokens to an actual AST? Well, that's our parser, right? And so our parser, the main thing that we have here is that we're going to write a function basically that inits a new parser. We once again make a type for the parser where it holds its lexer, it holds its current token, and its peak token. Notice these are not mutable fields. So these, each time we move one step further in the lexer, we sort of update our state, and we're going to create a new parser for that state. The cool thing about that is whenever you have one state, you'll always get exactly the next state. I'll show you how that works in a second. The primary sort of entry point for this function is probably unsurprisingly parse, and it takes in a parser. And so what are we going to actually do? We're going to try and collect all of the statements into a list. This is that sort of recursive accumulator pattern that maybe you've seen before from the previous video. But the idea is we start with an empty list. What we're going to do then is we're going to call this function recursively, where we're going to go inside here. We're going to say, hey, what's the current token? So what's our current token that we have, right? This is a token option. If we'll go over the sum case in a second, but in the none case, that means we're done. There's no tokens left. So we say, okay, literally, we're going to return the parser, and then we reverse the statements. That's sort of just because we build these up as a linked list. We reverse them. That's sort of a functional style thing. You can hate it if you want, but that's okay. It's maybe a topic for a different video as well. I think it's okay. So when we're done, we're going to do this. Otherwise, we're going to go here. And so what does this do? This says, hey, parse the next statement for me. And if we error, then let's like error out of this function. Otherwise, let's continue advancing the parser and adding this statement to the list of statements that we have. So what does parse statement look like? Parse statement says, hey, we've got a current token. Is it the let token? If it is, parse let. So parse let looks like this. And this pattern is basically the same for each of them. I'm not going to go over all of them, but this pattern is basically how each one's going to work, where you have this parse identifier, which takes in a T, that's the parser, and it returns a new parser and the identifier. So that's what it says it's going to do, or an error. And you're saying, I don't see any error handling, TJ. What are you doing? In the Go book, everywhere we have to have if error not equal nil, blah, 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 right? Or in Rust, maybe you'd see like parse identifier and you'd look like this or something. Well, that question mark syntax is actually handled by this let star operator. So notice normally we just write let. Let just says whatever this item is, put this here. But you can actually create sort of your own question mark syntax in OCaml by creating a new let star operator. And this basically says here's the result and the F. And if you know monads, by the way, they're a burrito. If you know monads, then you'll understand this maybe a little bit, but the basic idea is going to say here, and it's a bit complicated type to get started, but just walk through slowly. I promise it's going to make sense. You don't have to understand monads to understand this. What this says is that we have some alpha type and we have some error type, right? So we have some alpha. This is what happens when you return OK. And then we have some error type here, which is what happens when you return error. This says, hey, pass in a function here that takes in something of type alpha, right? So that's this alpha, and return to me some new beta type, and it has to be the same error type. So we're result. So it's kind of like map. It's not like map though, just to be clear. It's not like map because we only take in what happens if we got an OK value. And then what we're going to do at the end is we're going to return this new beta or error type. So let's go back to where we were so I can show you how this works. What this is basically saying is parse identifier this is the alpha type right here, which is going to return a new parser and identifier tuple. And so this says, okay, if this is returned okay, we're going to return a parser and a name. If it doesn't, we're just going to basically pass the rest through to whatever error happens from parse identifier. It's in a sense, you could write this like parse identifier and then parser, let x equals this in here, right? And so you'll see I have this as a match type, and we can call this with, we could pipe this to result.bind, and then pass in our own function, which says function parser name, and then do the rest of this. So it would be kind of a lot of extra work to rewrite. You end up creating a lot of syntax obfuscation, and instead we can do this idea where it's sort of like we're rewriting the function to use the question marks or like try, catch, or promise, resolve. All of those ideas are very similar, except OCaml lets you extend the language in these ways, and you kind of get used to it after you try it for a little bit. So this actually, every single one of these functions where you see a let star actually could fail, and we handle all of those failures by bubbling the error back up the stack as we go. So we try and get a parser and a name. That's this first part for right when you think about a let. This gets this X value right here. Then it says we better have an equal sign next. If we don't, that's an error. Then we say, let's advance the parser to the beginning of this expression, and then we're going to parse this whole expression. That's this parse expression. Could be a semicolon, doesn't have to be. And then return to me where we are now in the parser and this new let statement. This let statement is exactly the thing that I just showed you previously and tells you about the name and the identifier. So once we do that parse let, right, this is parse statement, so we'll keep hopping back up. It says, we have a new parser and a statement. Advance the parser so that we keep going, and then append that statement. So that would have put this new let statement in our list of statements. We keep on doing this as we're chomping down each of the things in our token stream, right? So we would have chomped this let, ident_x equals function, blah, blah, blah. And then if there was more stuff left, like let y equals true, then we would eventually get down to this let statement. And now we would be back at the beginning of this function, right? So we would have been right at this now let. And so now we try and parse the statement again, and we'd go in. And we just keep doing that. We keep doing it over and over until we get to the end of the list. And then it would say, there's no more tokens. So we're all done. Return the list of these. And now we have our AST. So take a deep breath, walk back. If you haven't seen this before, it's going to be a little bit different. But let's think about where we were. We start with a list of tokens, right? We take a string and we create this list of tokens. We can add new tokens as more language features evolve or whatever. That's totally fine. Once we have that list of tokens, we want to generate an AST. An AST, we just write out the different types of things we'd be able to expect. And then we write some parser to take that string, which is really take that list of tokens, which is inside the lexer, move forward as we go and turn that into a tree. So it sort of has to accumulate those nodes into these expressions. That's where parsing comes in. If you want me to talk about that more, let me know. But ultimately, the rest of the stuff inside of the parser is just writing out the different cases. You can see that we're just pattern matching on the different types of tokens we might have. We parse return. We're going to do the same parse expression. Parse expression is probably the most complicated part, but it's also some of the most elegant stuff that we have. What you can see here is we have this parse prefix, and we're once again going to use these pattern matching features that we have in OCaml to make things really nice. Match on the different types of tokens that we have. Maybe there's some unexpected ones, so we would need to return an error, and then we can parse on those. The infix, that's where there's a left and a right side. That's exactly what we talked about with the plus. And so you can see we match on something like, hey, if any of the peaks look like this, do this parse infix. If it looks like a left parenthesis, that means we're going to call. If it's a left bracket, that means we're going to index this. And you can sort of hop down each of these as you go and eventually get to where you're going to say, I see that now I have this like plus sign. And so I'm going to create this addition. That's basically everything about what happens in the parser. It ends up being a little bit more code. I have some tests at the bottom, but besides the tests, let's skip. It's maybe 400 lines of code, right? And that's the complete parser for this whole language to turn every situation that we have from the lexer into a valid AST. Obviously, there will be cases where people write illegal code. If you had done FN here and then done ASDF or something, this is not legal. So when you get to this function literal, I think we can probably find a function. Export parse function. We're going to expect a left parent as the first thing we see after we see this function. And if we didn't see this, this would return an error, right? So in the case where we have this, we'll be able to see this and we'd go through and say, we'll see that there's a left parenthesis, and then we're going to accumulate these arguments, and then we're going to expect that we get this left brace, and then we're going to parse a block, and then we expect that we get a right bracket at the end of that, and then we return our function. Same idea over and over and over. You just create a new token if you need it, figure out how you're going to handle that token. And this is where I feel ML languages, or at least languages with pattern matching, just make things so easy because you can just write these match statements. You can pull out variables if you need to. Like in this case for reading identifier, we actually just say if this matches some identifier, we can just return the identifier directly. That's like a really nice and crisp way to write that. So that's phase 2. If you have questions, if there's anything I missed covering, that's the general overview. And like the main conceptual thing I want you to understand is list of tokens to tree of nodes. That's the movement that we have here. Part 3 is when we start taking those nodes and evaluating them at runtime. All right, that's it for the video. See you later.